Hello world, it's me. In the last video, I discussed why old-timers feel the need to tie up fixed inputs to VCC with a current limiting resistor in simple logic devices. Like on this 8008 CPU board, this is part of my MilMod 8 reproduction system. This little 7474 flip-flop here, the D input is tied high through a resistor, a 1K, that's this guy. And up here there's a 74138, and one of the enables is just tied high through a 1K resistor. That's this one over here. And the short answer is that when you have devices like those that have a multi-emitter input, that current limiting resistor limits the emitter-to-emitter avalanche current if a voltage spike comes down the power or the ground rail. Well, in this video, this is a follow-up where we're going to talk about that very topic, meaning including a resistor in a fixed input specifically for testing or diagnosing the circuit. In this sketch of a flip-flop, for example, the preset and the clear are both tied high through resistors. And this allows you to come back to a fully populated board, and with a jumper you can just take either of these pins low if you feel the urge to manually force either a set or a reset of that latch. And of course you can only do that because this resistor is in place. And when I was doing that video, I used a little visual aid, the schematics for my Intel 820 microscope. Now someone watched that video, or at least enough of the video to make a very good argument that I misrepresented these examples in the schematic that I pulled from the microscope. So this video, we're going to revisit those examples to further explore what that viewer was talking about. And as I understand their comment, they didn't have a problem with an issue of any of the multi-emitter discussion that I talked about, but their issue was just about these examples that I happened to pull, and they said that I completely missed the point of the purpose of these resistors. And their claim is that in these Intel examples that I used, the current limiting resistors were not to protect the multi-emitter inputs of these devices, but the resistors were there specifically for testing of the circuit as a part of, the emphasis on the time of design for testing, design for manufacture, and automated test equipment. So in other words, this user thinks that this resistor are there for the exact purpose that I showed in this diagram. In other words, the ability to enable or disable that gate. So kudos to that viewer for noticing this and pointing it out to me. They obviously are thinking at a higher level than I was. And technically, these wouldn't have needed that resistor because these were from the 74LS family, and as we talked about in the last video, the LS family had outgrown the need for these current limiting resistors. So that presuming that Intel is not going to spend money putting in any resistor that isn't absolutely needed, or at least useful, what gives with this design of the NAND gate? There's another gate in this circuit that is going to completely make it obvious that the viewer was right. So before getting my dander up over the viewer's comment, it's high time to go back and look over these entire schematics and figure out the motive of Intel when they put these resistors in. So if we look on page 9, this is where it's going to become obvious. Intel was thinking on a higher level, and these pull-ups are indeed not for protection, but are there for diagnostics and testing. So what on page 9 makes this so obvious? Well, when I was looking at the NAND gate on the other two pages, I saw the extra one. I just presumed that they had an unused input that they didn't need like they did on this AND gate here, the 74LS11. So on those, that's where I first saw it, and that was just my presumption. I wasn't even looking on this page yet. But now it's obvious because this is the third gate inside A88, and A88 only has 3 gates. So from a design perspective, they weren't making do with whatever gates they had available. I mean, they didn't need a 3-input NAND someplace and were just using up the extra gates in the chip to avoid adding another 2-input NAND. They were intentionally using 3 inputs because these are all 3 of these gates. There's one there, and one there. Those are all 3 gates in A88. So when I saw that, I was really glad that I didn't start a beef with the viewer that he didn't know what he was talking about, because he obviously does. It's pretty apparent that unless Intel had a surplus of 7410s to use up, this was certainly a design feature and not an oversight. Since all 3 gates in that chip have that fixed tie-up input, it was certainly intentionally put in for diagnostics or testing. So let's look a little bit deeper into this. And in general, take a look at tying fixed inputs high or low, not to protect the input, but as a technique to enhance diagnostics, debugging, and testing of a circuit. The trouble with this on this Intel board is we're working backwards with little or no support documentation. I mean, I have the schematics for this and I have the user's manual, but that's really it. I don't have a diagnostics or any kind of a developer's manual. For this, Intel microscope 820, it's all going to be guesswork. But let's look at the rest of this circuit and see if we can make sense if we now view these as a diagnostic feature rather than just a casually put in pull-up resistor. While normally this is being pulled high, we can short this to ground as long as we do it in the right spot without damaging anything, because this resistor acts as a current limit. We have 5-volt rail up here. When we take the pin on this chip to ground, we've got 0 volts on the other side of the resistor. That gives us a 5-volt drop across the 1K resistor. So 5 milliamps of current, or 25 milliwatt being dissipated, and any little 8th watt resistor can take care of that, and so can any little trace. So you can see that we're able to pull this input low at any time just by shorting it to ground, and no harm, no foul. We're not going to damage anything. And since this is a NAND gate, anytime we pull this input down to 0 or false, then the output of that device will go high no matter what the other inputs are doing. And that's the key point. When we force this one input low, the values of the other inputs are immaterial, and it's just as if that portion of the circuit, everything leading up to that, didn't exist. So what would normally be characterized as an unused input is actually one of the most powerful inputs on this board, because it's a complete enable or disable of that portion of the circuit. As I mentioned, this could simply be done with a jumper wire if speed or timing weren't an issue. But since the current draw in this is only going to be 5 milliamps, a standard or a low power open collector TTL can easily override this pull up and drag that input low. The output of this gate could in fact be fully automated and driven from another TTL device. So maybe rather than jumpering that to ground, the intent was to jumper that to something else on this board, like maybe over on the output of the 8755. So maybe the processor directly could pull that high or low, or maybe there's another part of the circuit that you would use to override this portion of the circuit when you wanted to manually, or as another part of the circuit, control whether this is enabled or disabled. Or maybe the intent was to use like a dip clip on this guy and bring some of these off to a fully automated test station that could do diagnostics on this board and just tell you where the problem was, or tell you that it was operating as part of the quality control before you shipped to make sure that it was working right. Long story short, there's a lot of ways that we can override the normal output of this gate built in that current limiting resistor that allows us to just on-off switch this gate and enable or disable this output signal. From my experience, I would have generally have included an access pad to this for a pogo pin to make contact. If it was going to be part of an automated test stand, I would have had an access pad here that you would use a test jig, have pogo pins in it that would make contact to that, or at least a test loop or a test point pin for like a little DuPont jumper. Or somewhere on the board brought these together to a dip, and then you could have connected into that dip with these little dip to ribbon connectors. You could plug into a test dip here, and then this could have gone over into your automated test rig, and could automatically test these things. So I would have expected something besides just a resistor on this, at least some kind of marking so that we knew what was going on. So that's not much of an excuse. I just completely missed the purpose of these resistors. And on the microscope control board, I didn't remember anything being there in the way of a test pad or a test pin or anything of the like that would have triggered me to think test input rather than a normal current limiting input. Now I'm pretty sure that if I said there were no test points related to A88 on the microscope control board, then somebody would be able to prove me wrong. So I went ahead and disassembled one of my 820s to check it, and this time I'm going to take a complete set of photographs of this board so I don't have to take it apart anytime I want to look for something. Here is A88, and we can see that there are the 3 fixed resistors around that. Here's R24, here's R25, and there is R23. So there's no test points, there's nothing around here, which is a shame since there was room for, to put something else here. Or, at least what would have been nice would be some notation to indicate which end of these resistors was 5 volts and which end was the input pin. Since, obviously we don't want to take the wrong end of this resistor to ground, and I prefer clipping to a resistor when I can, since there's less danger of shorting to an adjacent pin if you're clipping directly to this. If you're using a dip clip, there's not quite as much of a problem, but I prefer to use the resistor if I'm going to clip something to this. It seems a little bit funny that, the same designer that put these pull-ups to make the circuit easier to diagnose problems would also then, in the same system, mount on the back a fuse that's buried so deep in the system that in order to change this fuse, you have to completely disassemble the system to replace that fuse. So obviously that fuse only blows if a crowbar, kicks it or something, but still they could have made that a little easier to change, or at least more visible, considering they did things like put in these override resistors. But, not to belabor the point, of course, but Intel was not known for making hardware easy to service. There is absolutely no test points that I can see anywhere on this entire 820 control board. Okay, well actually there is one over here. There is test point 1, which it's in such a prominent place you would think it was a ground connection for your scope or your logic, but you would be wrong. That's a logical assumption, but you'd be wrong. This test point is actually a trigger output for when a breakpoint is reached, and it's designed to trigger an oscilloscope or a logic analyzer. If we look here at how that fits in the 820, or where that's accessible in the 820, so this is the assembled, this is what the 820 looks like. That's that board right here. This is the system it came out of, and that's what it looks like when it's in the system. And so right back here in that little tiny hole right there is TP1. So that's that little test pin that you clip to for a trigger. So it's sort of accessible. It's in that little hole right there, and I guess it's a lot like noodling catfish, I suppose, except the post doesn't actually bite down onto your clip, but you stick something in there and you fish around until you grab a hold of something. And then, there's actually no ground connection to reference the scope. So hopefully you included a ground point on your system under test, because Intel sure didn't include a ground point anywhere on the microscope. So you see, this is why when you see a really odd design choice in an Intel board, so often the glaring, half-baked design choice decisions jump out at you, making it harder to see when an odd design choice was put in as a feature rather than an oversight. But I strayed off topic. Let's go back to the 2 nands. What we're going to do is actually look at those nands, figure out what's going on. Now that we know for sure that they were put in for a reason, we can work through this bit of the circuit to see what reason they may have been, see what reason Intel may have had in mind. So first, let's get a feel for the landscape of this part of the system schematic. Of course, you may not have, and you're probably not working on an Intel 820, but there's some good, generally useful insight that we'll see just by using this as an example schematic. So on the far right of this page, there's a pair of 2111As. They're 256 by 4 RAM, so we've got a byte of RAM here, 256 by 8 RAM, and they call this 2-port RAM up here at the top, which is what we would kind of call a pseudo dual-ported RAM. What they actually have are banks of multiplexers that direct address from multiple sources and also pass through the data from that source. So it's not dual-ported memory like what you're thinking, where you have 2 circuits simultaneously and independently accessing a memory device. It's a pseudo dual port where we have 2 parts of the circuit that can access that same RAM. And remember, this was designed in what the title box says 1977. So dual-ported RAM wouldn't even come along for another decade, I think. Sometime in the mid-80s is where we saw our first dual-ported RAM. And I guess Intel did have dual-ported RAM controllers before the actual chip-level dual-ported RAM came onto the scene. So before going down that rabbit hole, somebody can prove me wrong here, but I don't think that true dual-ported RAM came along until 1985 when I first remember it being applied to video and some higher end data acquisition cards. But I strayed off topic again. Whatever you call it, this 2-port RAM, this little block of 128 bytes of memory can be overlapped with the system under test, but it's also accessible by the onboard 8085. So either the system under test can access that RAM or the onboard 8085 can access that RAM. In addition, there's a third way to access that memory, and that's by a special request. Say when the system under test goes into a halt, when a breakpoint is reached, or when some other occasion occurs, there's a third way to access that RAM so you can go in and read it out and get kind of a status thing. So of course, allowing memory to be mapped onto the system under test is a fantastic thing. That was one of the big powers of this microscope. The user has control, you can access that memory as well as the system under test, so it allows the user to come in through their programming and change that. You can change in real time whatever data or program resides in that memory block. Here to the left of the memory block, so this is the RAM here, here to the left we have some multiplexers. And then to the left of the multiplexers, all of the other logic out here and the page that feeds this all determines which of these three entities, either the device under test or the onboard 8085 or the special application, which of those three entities are accessing this RAM. At this point, you should see the desire to have a bit of diagnostics. Let's say that for some unknown reason your microscope got a problem. For some unknown reason, this block of RAM that's shared by these three devices is becoming corrupt. So to break down the problem, it would be extremely useful to know who or which process was corrupting that memory. And there's a lot of logic. We've got a dozen pages of logic here in this microscope, and you can tell that the board's fairly sophisticated, lots of gates in here. And so it wouldn't take much of an error or mistake in the hardware or in the software to corrupt that shared memory. And by breaking down that problem using these gates, you could determine which portion of the software or the hardware was causing that corruption. So if pin 2 of this 74LS10, for example, is taken to ground, then this output is forced high, and so these multiplexers, which are for the internal 8085 access to that memory, are disabled, and so that 8085 can no longer access that memory. This other 3-input NAND prevents the system under test and the related circuits in the microscope from accessing that memory. So if we take that one to ground, the 8085 can't access the memory. If we take this one to ground, the system under test can't access the memory. Then if we go back to that third gate that was on page 9, this one, we see it's the same sort of situation. Here, there's a bunch of logic. All this logic controls the GIP output, and GIP means grant in progress. So where they say GIP on this, they mean grant in progress, and that's for, like I mentioned earlier, a breakpoint, an interrupt, or a halt, or something like that. So this grant in progress output comes back on this page. Here's the grant in progress, and we can see that that grant in progress signal comes up here to access when it is allowed to control that memory. Or basically, in this case, it just controls the address pointer for that memory bank. So these are all consistent. On all three of these NANDs, taking that pin to ground will prevent the respective source from controlling the address pointer and accessing that memory. So again, I can't say for certain that that's what Intel had in mind because I don't have any of their diagnostics or testing documentation for the microscope. But working backwards from the documentation that I do have, I can imagine that there's a lot of times that you're working on this thing that being able to selectively disable access to that dual-ported memory would be useful in doing the diagnostics on the hardware and writing software. Now another place I called out Intel on this was on this 8755, and I was throwing a little bit of shade because they took the chip enable and the I/O read high through a resistor. Well, obviously if the chip enable is pulled low, the input of the I/O read doesn't matter anymore. The bidirectional address data pins and the radio outputs will go into the tri-state mode. So this chip becomes completely disabled and all of the lines on this side will go into tri-state. And that would stop all communication with the 8755. No memory reads, no port I/O, no port configuration. The question is, if we're going to presume that this is in for testing and diagnostics, when would that be useful? Since this 8755 port is controlling the entire system, we look at these out here, these control the entire system. Maybe there's a situation where it's convenient to stop the software from updating any control outputs or reading any of these inputs. It's hard to envision that specific case, but it's easier to envision it being useful if you wanted to just swap out an 8755 or completely disable this 8755. Because if this 8755 were not configured after a reset, all of the ports will be in a high impedance input mode. And if the chip enable for this 8755 is low, then this chip will be entirely disabled just as if it weren't in the circuit at all. So you could use a dip clip, come off, and have just another board where an 8755 is essentially connected in parallel to this one, the only difference being that its chip enabled and IOR are not pulled low, they're allowed to float to go high. So you would have these two 8755s, and then by enabling one of them or the other one, you could just swap them back and forth, because all of these outputs would be tri-stated. If you do a reset on this and tri-state these, you could essentially have two 8755s in parallel and then flip back and forth which one you're using. The question is, why not just pop this 8755 out? They're all socketed, so it could be easily removed and replaced with a ribbon cable to an off-board ZIF socket where you could just easily flip these things in and out. So for some reason they thought that it would be useful to be able to completely disable this 8755 in situ. Maybe somebody can see exactly when that would be handy, but it just seems though it would have been easier to go to an off-board ZIF socket if you wanted to easily swap out that 8755. So that seems a bit of a stretch. My explanation seems like a stretch for that, and this it'd really be useful for one of these guys in the title box to jump into this conversation. I can't read any of their names down here, but you know who you are. You were the guys that designed this microscope 820. Let us know what's going on here. So that's about as far as I could pull these 820 schematics. I thought we might have a better luck with something that was designed for some progressive testing and diagnostics. And the first thing to come to mind would be Heathkit. So I pulled out the schematics for my Heathkit H19 and H89, and I said, surely in all of these Heathkit schematics, there's going to be some override input points that are used for diagnostics and confirmation of the circuit when you're building these things. Now when we go through this, if we find resistors that are a part of a bus, they don't count. They're just to make sure that the bus is terminated, or if something's not connected, or if nothing's connected to the bus. There's also some that are connected to jumpers. And so if it's connected to a jumper or a switch, like all of these resistor packs over here connected to the switch, those are obviously just pull up. So if the switch is open, those pulled up, those don't count. So anyway, I went through all the schematics I had for the H89, the H19, and any little clocks or other little kits that I've put together. And maybe somebody else has put together more Heathkits than I have, and they remember some of these override control points, but I couldn't find them anywhere in any of my Heathkits. So I was really surprised that Heathkit didn't have, some of these built-in fixed input pull-up resistors, to allow you to, set and reset latches or, counters or anything like that. So maybe somebody else has some examples of where they can find those in Heathkit. What would be, maybe a good choice would be some of the SAM's PhotoFax might have had that type of documentation if anybody's got access to a lot of the SAMs for vintage hardware. So giving up on Heathkit, I thought, well, another kit that, and is fairly well documented, is the SAW. So I pulled out the manual for my SAW, and if we look on some of the schematics back on, pages, I guess starting on X15 is a good page to start with. So this is X15, this is the schematic and bus. Here's the memory decoder, I/O, and the display section. And on a lot of these, we will see pole resistors on fixed inputs. So I had my magnifying glass. At some point you turn into your grandparents and your parents, and now I'm using my grandfather's magnifying glass that he used to sit there and read the newspaper and complain about the tiny print. So let's switch over to a digital version of these so that you can see what I'm pointing to. Now the vast majority of these inputs that are tied together, they're frequently things like latches, set and clears, and they're tied to the same pull-up. So at first glance it looks like they're really, signing up to the Motorola religion of tying absolutely everything through a resistor. When they have a whole group of these that are tied together and they seem to be completely unrelated, it doesn't strictly eliminate the possibility that they're for forcing the input, but it does make it more unlikely. And this is particularly true for latches, where here they're taking both the set and the clear, they have those together, and so if you were to do diagnostics on those and you were to take them, jump them forced low at the same time, it results in the unusual condition that both the Q output and the Q bar output will go to logic 1. And that's a nice trick, but generally it's not all that useful, and it's a bit dangerous since you never know how the Q and Q bar outputs will land when that set and reset are released. So the advantage of SOL that we didn't have with the Intel boards, and I couldn't find anything in the Heathkit system, is we've got a nice builder's assembly guide. If you go through the builder's assembly guide, there's some narratives for the theory of operation as well as building the system. And I didn't study this, extensively, but a few examples jumped out at me. So here in the schematic, you can see that U42 is taken high with quite a few other fixed inputs. But if you look at the builder's progressive testing, you can see they've got a diagram here, figure 3.6. They say take out the IC, bend out the pin, and reinsert the IC, and then ground that lifted pin. In that particular case, they were not thinking about testing when they pulled that pin with the resistor. So I perused the SOL documentation, and the only place I could find where the pull-up on a fixed input was definitively used as an override input was here in the video circuit where U2 and U13 resets are tied together through a resistor to 5 volts. And in this case, if we look at the manual, it mentions this in part of several different steps, to jumper one of these pins to ground, effectively clearing the latch. And this is done while the IC is fully inserted in the circuit, it's operational, and so it's not a once-off lift the pin, just like U42 earlier. They actually want us to come in and momentarily ground pin 1 of U2 and pin 5 of U75 in this case. So with U2 and U13 forced low because they're connected together, we just ground U2. The result of this is to set the cursor location counters back to 0, and these determine the starting cursor column and which row in display memory is going to be the starting row on the screen. And as you can imagine, resetting where the display starts outputting characters can be a useful trick if you're doing diagnostics. So perhaps somebody else knows the SOL better and can let us know if there's other points in the SOL that were designed in as some of these force level test points for diagnostics and testing. Since there's this one, we can presume that there's more. But then again, the way that all of their fixed inputs are pulled high through a resistor, that was the Motorola model where you just take everything through a resistor, and maybe even U2 and U13 were a coincidence rather than a design feature. Okay, well, I gave up hunting for better examples than that. I think you get the idea. If you're interested, you can look around in whatever documentation you have for whatever you're working on. And if you happen to find any that are very interesting, let us know in the comment section. Well, I appreciate your feedback on the last video that pointed out my mischaracterization in those examples and the microscope documents, and it encouraged me to revisit that and think a little deeper as to what the purpose of those were. But I'm still waiting to hear from anybody that has something to say about that asymmetric loading on multi-emitters, if they're pulled high or pulled low that I mentioned in that video. As always, if you found this video useful, things like a thumb up and subscribing are always appreciated. And fundamentally, the only encouragement there is to making new content. Talk to you later. Bye-bye.